So today I want to look at one of the problems that really was kind of foundational to the discoveries of calculus. All right, do you guys know the names of the two people who are kind of credited with discovering the foundations of calculus? Sir Isaac Newton is one of them.
And
Rene Descartes? No, he wasn't calculus.
I thought he was like
German, right?
Yeah.
He was German, yeah. Von Leibniz. Okay, Leibniz. And the interesting thing is, this is what makes it kind of so amazing. Newton discovered a lot of his stuff first, but he never published it. And then Leibniz on his own discovered a lot of the same stuff about, I think, 15, 20 years later, and he published it right away. And then Newton's like, oh yeah, well I figured that out a long time ago. So then he published his stuff. So there's this big debate about who actually founded it. And not that it matters today, but it's really cool that they were able to discover a lot of the same things. And there were also things that were not the same that they discovered or developed that kind of complemented each other's work. For example, a lot of the notation that we use even today, Leibniz came up with. Newton, he still used a lot of the traditional things that they were using at the time. Leibniz decided to make up his own notation to try to help out some of the, I guess, clunkiness of the work at that time. Okay? One of the problems, though, that they were addressing at that time was related to a field called optics. Okay? Working with lenses and mirrors and that sort of thing. Okay? People were trying to make glasses, for example, to help them see better, or maybe not make them originally, but they were trying to do a better job of that. Also, telescopes to see into space and all that kind of thing. But the problem was, there's a basic formula in physics. The idea is that when you're looking at things like light bouncing off of something, here's a surface, you have what's called this normal line. Okay, there's a normal line. Okay? And that's always perpendicular to the surface. Okay, and the reason why the normal line is important is because as you're looking at something reflecting, if it's coming towards the surface, there's an angle here, and we'll call that theta. And theta is what's called the angle of incidence. And in the study of optics, the common thing here is that the angle of incidence will be equal to the angle of reflection. Okay, so you have this reflection here. Oh, and I didn't draw it close enough to equal. That's pretty close to equal. This angle right here, we'll call that alpha. Alpha is our angle of reflection, and those are going to be equal. Well, obviously, if you're trying to do calculations and things, you got to be able to figure out what the angle is. Okay? And in order to figure out the angle, you've got to know where that normal line is. And you might say, well, that's pretty easy. It's just perpendicular to the surface. And that is easy. That is easy if the surface you're dealing with is flat. The challenge, however, is when you have a curved surface. Okay? And you have light or something reflecting off of that surface, say, right here. Okay? Well, where's the normal to that surface? We really have no idea. You got to figure out exactly what direction that thing is moving at, or that surface is going at that point, in order to then get perpendicular. And as a result, we look at this idea of the tangent line, because the tangent line tells us the direction we're going at that moment. And then once we have the tangent line, then we're able to get the normal to it. Okay? So, it's kind of funny because nowadays, more of our applications and things for what we're studying here are based on the tangent line. But really, the tangent line was just something that they found on their way to finding what they really wanted, which was the normal line. Okay? So that's kind of the history of where this came from. And what we want to present today is kind of the solution to how do we figure out what direction that function is going at that moment. Okay? So that's kind of the idea of where we're headed today, and this is the background to the problem we're addressing. All right? So we have the tangent line. The tangent line crosses a function at exactly 1 point. Okay? You guys know that kind of concept from geometry, but I want to take a quick look here at this diagram, because this is actually how they were able to develop this idea of finding the direction, or when we're talking about lines algebraically, what feature of the line are we really talking about? What determines its direction or its angle?
Slope.
The slope. Okay, good. The slope. All right. So we want to find the slope of this tangent line right here. Okay. But you guys know in order to find slope, you have to have 2 points, right?
Yes.
Because you do the change in the y's divided by the change in the x's. Okay? So your slope is change in y over change in x. There's your formula right there. Okay? So in order to figure that out, obviously when we have a tangent line, there's only 1 point that's actually on the function. So what we decided to do is we took this point, and the scan's a little bit bad here, so I'll fill it in. This is the point, some value of xc, and then we plug that into the function, so the y coordinate is f of c. Okay? And then we take another random point on the function. Okay? And I'll make this one blue. Now, to get there, we just use some kind of arbitrary distance, this delta x. Not sure how far that is exactly. It's just a change in x. That's what the delta represents, change in x. Okay? Well, that means we took the c, which was our x coordinate, and we added that delta x to it. All right? And then, of course, to get the y coordinate of that function, you have to evaluate the function for c plus delta x. Okay? Does that make sense? Yeah. All right? So, now we have 2 points, and we have what's called our secant line. All right? Now, again, this goes back to kind of your geometry knowledge. The tangent line intersects at 1 point. The secant line intersects at 2 points. And the nice thing with that is that we can now find the slope. Okay? So, we said here, the slope is the change in our y's divided by the change in our x's. So, we would subtract. And you'll notice here the change in our y's is going to be the y coordinate f of c plus delta x minus f of c, the y coordinate at this point. Okay? So as we do this, we can now recognize that the slope of that secant line is f of c plus delta x minus f of c, all over c plus delta x minus c, which, notice in the denominator, the c's cancel out, and we are left with that. F of c plus delta x minus f of c all over delta x. Okay? This formula right here will give us the slope of any secant line. Alright? You might say, well, what good is that? Question?
Is the green line the secant line?
Yes, the green line is the secant line. The red line, that's the slope that we actually want. That's our tangent line. Okay? Yeah, so that's our secant. And the red, that's our tangent. That's our goal. We want what the slope of that is. Okay? So, in order to find the slope of our tangent line, we find the slope of some random other line. How in the world is that helpful? Okay? Well, what they found was this delta x was arbitrary. We just picked a random distance here. However, notice if we were to move this point a little bit closer to the point that we have our tangent line at, let's say we made it here, okay? If we were to draw this secant line, its slope would be still not the same as the tangent, but it would be closer, right? And what if we brought this point even closer? Yeah, it'd be almost the same, okay? Now, notice what's happening here each time we move the point closer. What's happening to delta x? It's getting smaller. And in fact, if it keeps getting smaller, what concept are we dealing with here? A limit. Not squeeze theorem here, but the limit. The limit here is what we're working with. All right, check this out. This is kind of a couple of different pictures illustrating it as delta x gets smaller and smaller. Okay, remember in each of these instances, here's our tangent line, here's our tangent line, here's our tangent line, and you can see, obviously this one has the tangent line, but as that point gets closer and closer and closer, the slope of the secant line is approaching the slope of the tangent line. So we take the limit as, you can see right here, delta x approaches 0. Okay? We're going to end up taking the limit as delta x approaches 0. Question?
So what if you have like an absolute value and there's no like other point to like grab a tangent, like not to find like a secant, to find like another point next to
it? Okay. You're talking about like the point on the absolute value?
Like if you want to find like a tangent line to like the one point there.
That's going to be a point where we would say it's not defined. Because there's an infinite number of lines that you could draw through that one point. That gets into differentiability, which we'll talk about later. Is it possible to do this, basically, is what that's saying. Okay. So we take this slope that we found of the secant line, and we're now going to take the limit of that as delta x approaches 0. And this gives us the definition of the tangent line of slope m. Okay? We're going to use the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x, and that equals m. Okay? Now, we did something a little bit similar to this. Those of you who had pre-cal honors, and those of you in SL, we did something similar to this. This is a specific one for a specific point. We're going to get to doing the general ones, which are all that we did very briefly in those other two classes, okay? So, the slope of the tangent line, just a matter of terminology here, the slope of the tangent line to the graph of f at the point C, f of C, is also called the slope of the graph of f. Okay, so you can kind of use those terms interchangeably, the slope of the tangent line or the slope of the graph of f. Okay, those terms are basically synonymous here. Okay? So, let's actually look at using this definition. Okay? So, example 1. I'm going to write down that definition we just developed here. The slope is the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. Okay, there's our definition. So, our first example here, find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. Now, my first question is, why is this kind of an odd problem to solve? It's linear, okay? So what's the slope of the graph at the point 2, 1? It's 2, just like every other point on the line, okay? So the reason we're starting with this one is it's because it's kind of easy to do, and we can also verify our result based on stuff we know already. All right, so we know m is 2. Okay? Don't forget that. That's what we should end up with. But let's look at here the process of finding that answer. And the reason why we're doing it with this one is it's a simple function to solve for, but the process is the same no matter how complex the function gets. All right, so I have our equation over here. So now I'm going to be taking the limit as delta x approaches 0 of, what's c in this case? Alma? 2. Okay, that's c. So f of c, 1. There we go. Okay, so let's think this through here. We have f of 2 plus delta x minus f of 2 all over delta x. Okay. Now, we already know what f of 2 is. So as we're taking the limit as delta x approaches 0, we're going to be subtracting 1 here. The question is, though, what is f of 2 plus delta x? Now, I prefer to find this on the side. It saves me having to write that whole limit thing over and over and over again. So I do that part over on the side. You can do it right here if you want, but f of 2 plus delta x, I'm going to take the 2 plus delta x and I'm going to plug that in for x. So I have 2 times 2 plus delta x minus 3.
Where's your two? What? I didn't get.
Okay, let's look at that closely here. 2x, I'm replacing the x in the function with 2 plus delta x. Do you see that?
But I thought you said it was -1, not -3.
Oops, hang on. The original equation is 2x minus 3. Okay? Notice all I'm doing here is I'm trying to figure out what to plug in for this f of 2x f of 2 plus delta x. Okay, so this right here, I'm just figuring out what this is, so I don't have to rewrite all this stuff as I do other algebra. Okay? So, 2 plus delta x. Alright, so let's simplify that a little bit. This is 4 plus 2 delta x minus 3. That's a 1 plus 2 delta x. So now I've done all the algebra to simplify that, and I can now plug that in right here. 1 plus 2 delta x is f of 2 plus delta x. Alright? So now we're simplifying. Our slope is the limit as delta x approaches 0 of, notice this is now 1 minus 1 is 0, so we're left with just 2 delta x over delta x. So the slope is the limit as delta x approaches 0 of 2. Because the delta x's canceled out. Okay? And what's the limit of 2? 2. The limit of a constant is the constant, so therefore it's 2. Alright? So now we figured out what we already knew, that the slope was 2. Does anyone have any questions about our process here?
I just have maybe like I wonder if you can just do like in the second step f of 2 plus delta x. Can you just do f of 2 plus f of delta x?
That's a good question. Can you do that, guys? If you have f of 2 plus delta x, can you just make that f of 2 plus f of delta x? No. Okay. It's not, we're not distributing the f, that's function notation, so it's f of the whole thing. Okay? That's a good question, I'm glad you asked that, but we can't split it up that way. Now, one thing I do want you guys to recognize though here is every one of these is going to be an indeterminate form. 0 over 0. If I plug in 0, I'm going to get f of c minus f of c, 0 over 0. Okay? So, think about what we looked at in our last unit here with indeterminate forms. You may have to rationalize, you may have to factor and cancel out the whole, or something like that. Or you may even run into those ones that we memorized, remember the limit as x approaches 0 of sine of x over x. Okay? You might have sine of delta x over delta x or something like that at one point. So you may have things that you had to memorize, but a lot of these is you're going to be rationalizing or factoring or whatever, but you're handling those the same way we did the others, okay? Don't let the fact that we have delta x's in there confuse you, okay? It's just a variable. Alright, so let's try a second example that we don't know the answer to right off the bat. Okay, here we have the quadratic equation x squared plus 1. And we're going to actually do this twice. The first one here, we're going to find the slope of the tangent line at -1, 2. And then secondly, we're going to find the slope of the tangent line at the point 0, 1. Okay? So we'll do this twice. Let's do the first one together. I'll let you guys do the second one on your own here. So the one in blue at c equals -1. Okay? we have the slope equal to the limit as delta x approaches 0 of f of -1 plus delta x minus f of -1 all over delta x. So at this point, we need to figure out what f of -1 plus delta x is. F of x is x squared plus 1. So, -1 plus delta x squared plus 1. We need to then simplify. What do we how do we simplify? Foil, okay. Don't forget that easy stuff. Alright? That's the kind of stuff that'll drive you crazy because then it won't work out right. Remember to FOIL. So 1 squared, -1 squared is 1 minus 2 delta x plus delta x squared. And then we have the other plus 1 there. So now it's 2 minus 2 delta x plus delta x squared. Okay? And by the way, what is f of -1 as well, since we need that? 2. Okay, it's the point, -1, 2. Okay? So, now that we have that, we can continue on here. Limit as delta x approaches 0 of the 2 minus 2 delta x plus delta x squared minus f of -1, which we just said is 2. And that's all over delta x. 2 minus 2, of course, is 0. And what do you notice about our numerator now? Very good. There's a common factor of delta x in the numerator here. So limit as delta x approaches 0. We have a delta x in the numerator that we can factor out and then cancel with the delta x in the denominator. Okay? I'm writing it all out. If you see it and you can do it carefully and correctly without writing out that whole step, that's fine. Okay? But now we're taking the limit as delta x approaches 0 of just say -2 plus delta x. So what does that equal? Yeah. Now we have something that we can simply evaluate. Plug the 0 in for delta x and we get -2. Okay? Now, don't forget to make sure your answer makes sense. Okay? Look at the tangent line. Does it make sense that the slope is -2? Yeah, it's going downhill. Alright, at least make sure you got the right sign, okay? It's going downhill pretty steeply, so it's -2 there. Okay?
Can you zoom back over real quick?
Yeah. There we go. Okay? So, you take a couple minutes here and go ahead and try finding the slope at the point 0, 1. Okay, the second of the 2 points here. Okay, find the slope of that tangent line at 0, 1. Alright, let's take a look. Alma let us borrow her work here. And notice, she plugged in 0 for C, and f of 0 was 1. Okay? Also, when you plug 0 plus delta x into x squared plus 1, you just get delta x squared plus 1. The plus 1 and minus 1 cancel out, and you have a delta x squared over delta x, which is delta x. Once you cancel this out, right there, that's where you're getting rid of the whole. Okay? You're canceling out the whole here. Okay? Because that's 0. Alright? But now the whole is gone. Okay? Remember, the whole is what made it 0 over 0. Okay? Once you get the whole gone, then you can simply plug the 0 in. Okay? And you get 0 for the slope. Okay? Now, as we work through this, as we develop further into this, we will develop rules that make this a lot easier. Okay? But we do need to be able to find this way as well, okay? And notice just an example of this. In this function, the slope at any point where the x-coordinate is c is going to equal 2c. So the point -3, 10, the slope is going to be -3 times 2, so -6. At the point 5, 26, the slope is going to be 2 times 5, 10. Now that's just for this function. Right? We'll develop rules for figuring it out pretty quickly for other functions as well. Alright? But that's all for this.